Good morning. Thank you for the opportunity to give this presentation. My name is Alan Salcedo Gomez, and today I will talk about the assessment of the SCAN and regularize the SCAN functionals with and without self-interaction correction. This was the topic of my undergraduate thesis work, and this work was supported by the US Department of Energy. So we know that SCAN was the first non-empirical functional designed to satisfy the 17 exact known constraints for semi-local functionals. And although it does not work pretty well at predicting magnetic properties, it is still one of the most successful meta-GGAs used for electronic structure calculations. Such is its success that we have been recently interested on how it performs with self-interaction correction methods. However, the implementation of SCAN in DFT software is already very challenging, as we need that exchange correlation energy converges with respect to a radial mesh. And the implementation of this radial mesh has to take into account any numerical instabilities that the functional may have. So it is indeed documented that SCAN suffers from numerical instabilities, which are caused by the use of the iso-orbital indicator function. So some modifications have been proposed in the past to improve these numerical problems of SCAN. One of them is the use of an improved iso-orbital indicator function itself. And a second one was taken last year by Bartok and Yates, and it consisted on regularizing the functional form of SCAN. And this will be the focus of this talk. So they proposed to modify the iso-orbital indicator function alpha by shifting the value of the kinetic energy density of the uniform electron gas by a small constant so that it behaves nicely. But most importantly, they proposed to modify the enhancement factor of SCAN, which depends on this switching function fx of alpha, in which for SCAN it has been constructed so flat in this region to maintain this low varying limit constraint. So they identified that this region, when we take the first and second derivatives, it shows these numerical oscillations, which are difficult to capture when doing numerical integration, unless we use very refined numerical grids. So to get rid of these oscillations, they proposed to replace the switching function in the region between alpha equals 0 and 2.5 by a 7th degree polynomial that's smooth and continuous at the edges and vanishes at alpha equals 1. Of course, while they do this, they are breaking this low varying limit constraint. So at UTEP, we implemented the SCAN and rSCAN functionals in the UTEP NRL mol code, and here we show the numerical instabilities of SCAN by plotting the energy landscape of an NaCl dimer as a function of its bond length. And for a grid density that's usually sufficient for PV calculations, we see that this energy curve has discontinuities which compromise energy convergence. And as we increase the grid densities, although these discontinuities disappear, these energy curves go very slowly to this finally converged energy given by this dotted line. So when we recalculate this using rSCAN, we see that the numerical discontinuities mostly disappear and that the energy curves converge much faster for less refined grids. So we also calculated the vibrational frequencies for water clusters. Vibrational frequencies, well, a vibrational frequency is a property that's very sensitive to the properties of the grid. So we use SCAN and rSCAN to calculate the vibrational frequencies of a single water molecule, dimer, trimer, and that we see that SCAN and rSCAN show basically no difference. For the tetramer, we see small differences here and here. And interestingly, for pentamer, although we use a very refined grid for SCAN, it still shows this imaginary frequency here, which rSCAN has corrected. And this table basically summarizes the errors for SCAN and rSCAN in comparison to very accurate calculations. And this final column shows the difference between SCAN and rSCAN calculations. We also calculate the electric dipole moments for the Head-Gordon dataset, and we see that when calculating the mean absolute errors and root mean squared errors, SCAN and rSCAN show similar performance. We also calculate the magnetic anisotropy barriers for the following 4 molecular magnets, and again we see that SCAN and rSCAN show similar performance and that they both predict the correct spin. We know also that density functional approximations suffer from self-interaction errors. And that's caused by the fact that the self-Coulomb energy is not properly cancelled by the exchange correlation functional. And the existence of this self-Coulomb energy is noted when we see that the Hartree functional does not vanish for one-electron systems. So in 1981, Professors Perdew and Zunger proposed to add the following correction term, which properly cancels the self-Coulomb energy and self-exchange correlation energies in an orbital by orbital basis. And here we use a set of what are called the Fermi orbital descriptors, which is a set of positions in space that are used to modify the Kohn-Sham orbitals obtained from DFT calculations to turn them into what are called the Fermi orbitals, which are later orthogonalized using the Lowdin scheme, obtaining the Fermi-Lowdin orbitals, which are used now in combination with PZ-SIC equation. And to this method we call Fermi-Lowdin orbital self-interaction correction, or FLOSIC. We also calculated the large C-limit behavior for rSCAN, as done by Perdew and Santra for other semi-local functionals, and we observe that although rSCAN violates this low-varying limit constraint, SCAN and rSCAN show similar performance at the large C-limit. We know that SIC calculations are around n times more expensive than DFA calculations, where n is the number of electrons in the system. And because SCAN requires more refined grids, SIC calculations with SCAN may become even more expensive. So we think that rSCAN may be a solution to this problem. So now we are interested on the performance of rSCAN with and without SIC. And for our computational method, we use the FLOSIC code, which is based on the UTEP and NRL MOL code, which are both developed in the UTEP group, which uses PZ-SIC in combination with Fermi-Lowdin orbitals. These are the orbital basis set, and then we note that SCAN calculations use much more refined grids than rSCAN calculations. So now we assess the performance of rSCAN with and without SIC for a wide range of electronic properties for atoms and molecules. First, we calculate the total energies of atoms for between hydrogen and argon using both SCAN and rSCAN, and we compare these results to reference values and we obtain mean absolute errors. And we see that at DFA, rSCAN increases the mean absolute errors from SCAN by a few millihartree, and it decreases the mean absolute errors by a few millihartree when turning on SIC or FLOSIC. We also calculated the vertical ionization potentials for a small data set of atoms between helium and argon, and for a larger data set of atoms between helium and krypton. Then we compare these results to experimental values from the NIST database, and we obtain mean absolute errors. So we see that the mean absolute errors, both with SCAN and rSCAN, are very similar at the DFA and also when turning on SIC. And similar results are shown for the larger dataset. Similarly, we calculate the electron affinities of atoms for the first 12 open shell elements, and we see again that SCAN and rSCAN show similar performance at DFA and also when turning on SIC. And finally, we do the same thing for the first 20 open shell systems. We also calculate the atomization energies for the AE6 test set, which is composed of these following molecules. And then again, we calculate mean absolute errors, and although we see that rSCAN increases the mean absolute errors from SCAN, this mean absolute error is still very low in comparison to calculations using PBE. However, when we weight these values and calculate mean absolute percent errors, we see that SCAN and rSCAN show similar performance both at DFA and with FLOSIC. We calculate also the reaction barrier heights for the BH6 test set, and again calculate mean absolute errors, and we see that SCAN and rSCAN show similar performance at DFA, but the mean absolute errors are much closer when turning on SIC. Finally, we calculate the dissociation and reaction energies. First, the dissociation energies of the SIE 4x4 set, which is composed of these four positively charged dimers at these given separation distances, and we see that the mean absolute errors of both SCAN and rSCAN are similar at DFA, but they go down by a whole order of magnitude when turning on SIC. Similarly, we calculate the reaction energies for the SIE11 test set, which is composed of 11 reactions directly affected by self-interaction errors. And again, we see that SCAN and rSCAN show similar performance at DFA, and the mean absolute errors go down by a half when turning on SIC. So in summary, we studied the performance of rSCAN with and without SIC. And for a wide range of electronic properties, rSCAN shows similar performance to SCAN, with the exception of the atomization energies. Interestingly, in the case of barrier heights, dissociation, and reaction energies, we see that SCAN and rSCAN show similar performance even with self-interaction correction or FLOSIC. And finally, we note that these rSCAN results were obtained with around 50% of the grid points used for SCAN calculations, which may be improved in the future. So here we show a picture of the FLOSIC collaboration, which is composed of these institutions and these people. And this is the group at UTEP. And this is a picture of the University of Texas at El Paso. Thank you.